Hey class, this lecture is going to be on resolution or resolvence or diffraction grading, how we're able to resolve images. So we're looking at Unit 9B, Objective 8, where we can determine if 2 points can be resolved using many forms of apertures. We haven't seen the word apertures yet, but that word pretty much just means an opening. So that may be a slit, or a hole, like a hole or something like that. And when we start identifying where we have slits, we're looking at like single slits. We have holes. We have very much circular apertures, such as telescopes or even our eyeballs are considered an aperture as well. Using that, we're going to solve problems involving the Rayleigh criterion for light emitted by two sources, and we're going to calculate resolvence of diffraction gratings. But first, let's start with the warm-up, in which we remind ourselves of diffraction grating. And we have a diffraction grating that's 2,000 lines per centimeter. And the question is, at what angle will the second order maximum of a 520 nanometer wavelength light? So we have a second order, and we have 520 nanometers. We've also got a diffraction grating that's 2,000 lines per centimeter. So we need to remember the equation we use for diffraction grating, which is in our data booklet. N lambda over d is equal to sine of theta. And we have n equals 2, lambda is equal to 520 times 10 to the negative 9th meters, and d is the distance between the slits, but we need to come up with that using the diffraction grating lines per centimeter. Now this is lines per centimeter. We've seen lines per millimeter more often, and we need to convert this into meters per line. So if we had 1 centimeter, 1 times 10 to the negative 2nd meters, we would have 2,000 lines. And that's how we convert it to meters per line, and which is just the distance between each slit. If we solve for this, we should end up with 5 times 10 to the negative 6 meters, and that should be our d. So our d is 5 times 10 to the negative 6 meters. And let's solve this. So I have 2 times 520 times 10 to the negative 9th divided by 5 times 10 to the negative 6th equals sine of theta. So I'm going to have to inverse sine this whole value right here. And I would end up with a theta of 12.0 degrees. Make sure that you're in degree mode if we want to find degrees. You can also find radians and find the angle in radians, but degrees is more friendly. And then we have a next question, which is at what angle will the second order maximum of a 540 nanometer wavelength light? I'm going to pause this video. I want you to just solve this on your own. All right, so get ready for the answer. It's the same. We just change 540 into 520, and we get a theta is equal to 12.5 degrees. Now, why did I ask you to find these two angles, like 520 and 540 nanometers, and they're so close? And it's because when we have two of those wavelengths passing through, when can we actually separate those lines on the screen to be separate? Because it's 12.0 and 12.5 degrees. So like our angular separation, oh, that's not theta. The angular separation is 0.5 degrees. And so is that enough to where we can actually identify and say, yes, that is a 520 nanometer wavelength, that's a 540 nanometer wavelength? Or are we not? Does that look like one, are they constructively interfering and we're actually just seeing one band of combined light? So that's what we're going to do today. And that's one of the things we're going to process for us. So what defines the ability to see things? Well, we're looking at telescope images. One of an old telescope. So this one was like a older telescope. And this is a newer telescope. And what can you see is different between these two images? So in this image, we don't see colors, and we also just don't see a lot. It's just kind of very poor resolution. Where in this one we can see colors, and we can kind of see the spacing between the colors as well. Like we actually see the spacing in between the red. So when we have the ability to resolve things, there's two things we're going to focus on. We want to see, like, can we see color, and can we see objects, or spacing, or pixels if we want to bring about digital cameras into the mix. And so this shows up in two ways. One, with the color that we see in these images, and two, what we use every time we go into, if you need to get glasses and go get your eyes checked, is when can we really stop being able to see this E as an E, or which direction is the E going. And that is going to be the difference between seeing different objects, whereas this is the difference in being able to see different colors. So we're going to go and look at color first and say, how can we resolve different wavelengths? And then we're going to say, when can we have the ability to resolve 2 points as individual points, and therefore being able to see if this E is looking up, right, down, left, and not just a dot on the screen. So first, with colors, we just need to look at the concepts of resolvance in relation to being able to see different colors. And we're going to use this diffraction grating to do that, because diffraction grating is one of those nice technologies we use where it separates the colors for us. And we have different bands of light, similar to what we just solved for 520 and 540 nanometer bands. We want to see when are we able to separate those two as different bands of light. And when I say bands, I mean like this is a band of light right there. Although it didn't focus. That's a band of light. These are bands of light. So the resolving power of a diffraction grating is the numerical rating that the diffraction grating has to be able to resolve or separate wavelengths, or see these separate wavelengths. And this is R is equal to Mn, where M is the order, like order on the screen, and N is the number of lines that light is incident on. And that would be found on our screen, where if we had a light shining ahead onto the screen, we could look and say, there's this, how many lines are in between that light ray. Now, that tells us the resolving power of the grating, but that doesn't tell us if we're able to resolve specific wavelengths. So we need to determine what power we need, what resolving power we need for certain wavelengths. That resolving power that we need, so R that's like needed, is equal to lambda over delta lambda. And what they don't tell you, this is in the data booklet, but what they don't tell you is that this lambda on the top, the best one to use is if you take an average, because we're going to compare two wavelengths and find the difference between those wavelengths, find the average of those wavelengths, and then by dividing those two values, we're going to end up with the needed R. So for example, the problem that we did on the top with 520 and 540, our average would have been 530, and the difference would have been 20. So we could have found the resolving power needed by dividing the 530, right? 530 divided by 20, and that would be your R needed for that problem up above. But we're going to do a practice problem later, so I'm saving that till later. There's one thing that the data booklet doesn't tell you, because this is in your data booklet right here. The only thing that's partially wrong about this is that I said this is an average, but we also see a lot of equal signs. But that's technically not true, because this M is the resolving power of the grating, and this lambda over delta lambda is the needed resolving power. So that means in order for the diffraction grating to help us resolve these two wavelengths, or to be able to see separate wavelengths, our Mn has to be greater than our lambda over delta lambda. And then if this is the case, if this is true, then we can resolve the two wavelengths. So I should say if this is true, then we can see the two wavelengths. So let's do a practice problem. We have two lines in the emission spectrum of sodium that have wavelengths of 589 nanometers and 589.6 nanometers, respectively. Calculate the number of lines per millimeter needed in a diffraction grating if the lines are to be resolved in the second order spectrum with a beam of width 0.1 nanometers. So there's a lot of information being given. First, we have our wavelengths. That's going to help us with the left side, with the needed resolving power. But the resolving power of the grating means we need to get to a lines per millimeter and with a beam of width 0.1 millimeters, assuming we're in the second order. So if I were to identify what variables I have below, I would say, okay, I know my my wavelength average is 589.3 nanometers. My delta wavelength would be 0.6 nanometers. And then my order is M, so that's my second order. And you might be like, what the heck? We just called it N. Why the heck are we calling it M now? And I feel you. I don't understand it either. But according to IB, we use N when we use diffraction gratings. But for some reason, when we get to this point, I guess they didn't want to deal with like N, capital N, so they made it M. But I'm sorry. Well, that's what we want to find. But we want to remember that this is the number of lines like that the light is incident on, or the number of lines hit by the light. So there's going to be some trickiness with that, but let's just plug some numbers in, get to what N should be, and then try to see how to get to lines per millimeter. So in order for our wavelengths to be resolved, then my Mn, my resolving power of our grating, has to be greater than the resolving power needed, which is lambda average divided by our delta lambda. So I have 2m, 2 as m times n is greater than 589.3 divided by 0.6 nanometers. But since it's the same on the top, those will cancel out. So I end up with n is greater than 491 lines. Now this is the number of lines that the light beam is incident on. That means when light is traveling, like if light is traveling right here, and that distance is 0.1 millimeters, then we should see in that distance 491 lines. So how do I get lines per meter in this case, or in this case, lines per millimeter? Well, I just need to take my number of lines incident divided by the width of light. And so I get 491 divided by 0.1 millimeters. And so this is just 4,900, we'll just say 4,900 lines per millimeter. So I rounded, right? Technically it's 4,910, but that's it. And that's where we would end off. So like this, end off with our answer. Okay, so using diffraction grating, depending on how many lines per millimeter there are and how many orders we are looking at. So the higher the orders, the easier for it to be observed, and the more lines, the easier for the wavelengths to be observed as well. We can determine how strong we need our diffraction grating to be to resolve two wavelengths. That's how we resolve different colors. That's why when we look at this image, by looking at different orders available and looking at and increasing the amount of lines per millimeter, we're able to actually observe these differences in these colors in this image. And the stronger we are, the more we can actually observe different wavelengths that we're looking at. The next one, though, is how are we able to see two different objects? Because when we look at this top one, how do we know it's an E? We know it's an E because this portion is separate from this portion, is separate from this portion. So we're actually noting that there is a space right here that we can see. So what tells us, or what makes us not be able to see that E? It's when we stop being able to see that space. So I want you to think of this as 3 points. Let's look at it as a blue point, an orange point, and then another blue point. And forget about colors, though. I just can't draw a white point. So my orange is my white point. For us to be able to see both a blue, orange, and then blue, that tells us that this is an E. Because then we can see there's a line, then a space, and a line. But at some point in time, this is going to happen. The blue is going, well, actually down here, this, once I'll tell you how far I can see. Well, obviously down on number 8. But like if you look at number 2, at some point in time, the blue points are going to overlap and we're going to stop being able to see that orange point or stop being able to see that open space. I see that down at number 8 where I just can't tell where the heck it's going. And that's also, of course, a problem with the resolution of this image, but it also occurs when you're at the eye doctor and you're looking at the same diagram and you can't see the direction that the E is going. It's because you can't see the white space because the 2 points are overlapping. So our ability to resolve 2 different objects or 2 different points in space is where we're looking at next. So this image is the best type of image that we are going to use to understand when are we able to see an object as 2 separate objects. And the resolvence is the ability for an image system to be able to produce 2 separate distinguishable images of 2 separate objects. So for example, this one is definitely 2 separate objects. This one is like barely 2 separate objects. And that's the moment that it becomes 2 separate objects. And this is just 1 object. So let's say 2 objects, maybe 2 objects. And this is definitely not. This is 1 object, or not 2 objects. And so we're going to use a single slit aperture or our eyes or telescopes to help us observe these images. And we're going to use what's called Rayleigh's criterion to identify the moment in which it becomes a separate object. So for example, in this image, we can see those 2 objects as 2 separate objects. And if we were to observe these images using a slit, we would see a single slit interference pattern from the light traveling through the single slit and hitting a screen. And another light would also travel through, hit the screen, and pass right through and see another interference pattern. So we see these as separate images. And on our screen, or for example, on the back of our eye, where these images travel through, we see them as 2 separate images. At some point in time, though, they become just on the brink of becoming 1 image, or vice versa, just on the brink of becoming 2 images. And this is when we call something as just resolved. That's the term, just resolved. And that occurs when the maximum, the central maximum of one of the images matches, right, with the minimum, the first minimum of the second image. So that means the distance between these 2, the distance between those, are equal to the distance from the central max to the first minimum. And that's going to sound familiar because that sounds like the single slit interference equation. So we want to remember that. And of course, images are unresolved when the images completely overlap. So Rayleigh's criterion says 2 sources are just resolved if the central max of one diffraction pattern is no closer than the first minimum of the other. So if we were using a single slit, what is the minimum angular distance of the 2 objects if they are just resolved? So we know that the angular distance between them, theta, for a slit, must be greater than or equal to this Rayleigh's criterion, in which the distance between each other must be equal to the distance from central max to first minimum. So that means that we're using the same measurement for the theta, such that their distance is separated by this central max to first minimum, where b is the slit width and theta is the wavelength, like the observed wavelength. So when looking at that on a screen, how does that look like? Well, if there's two objects that are separated by some theta angle, that theta angle should be equal on the opposite side of the aperture, the circular aperture, which in this case it's a circle. And when we observe their interference patterns on a screen, we would see that the central max to first minimum are equidistant from each other. And that's where that theta, that's our theta, that makes the difference of lambda over b. And so once it's greater than that angle, then we can see them as separate images. If theta is less than this angle, then these two interference patterns would overlap. So they need to be separated by some distance, theta. Now, this is for a slit. So something to note is we have referenced this part here as our kind of Rayleigh's criterion, but for a slit. But in your data booklet, you're going to get this equation where there's a 1.22 factor in front of this lambda over b. And that's because we're not looking at slits anymore. We're often going to look at circular apertures to measure these two objects, because when we look into space and we're separating two objects in space, we're using a telescope. When we are looking at those E's, for example, in our eye doctor's appointment, we are using our eyes, which have pupils, which are circles. So the other form of apertures are eyes or telescopes. And that is going to be this equation. Now, they also say this theta is equal to, but then again, that's just another issue with IB, because technically there should be a greater than or equal to 1.22 times lambda over b, where b is not a slit width anymore, it's the diameter of circular aperture. So this could be, like, for example, the pupil diameter, or I'll make this a little bigger, or diameter of telescope, of a telescope. Those are some examples of what we could use for B. All right, so one key point we need to recognize is this theta. We're not using a sine of theta anymore. So we're going back to that small angle approximation. That is due because we're actually pretty darn good at resolving images. Try to imagine, look at a wall and try to identify two closest points on the wall. And try to think about the angle between those 2 points from your eye. Right? That angle has to be less than 1 degree. We're pretty darn good with our eyes, and similarly, we're pretty good with telescopes too. So this theta right here is definitely less than 10 degrees, and if that theta is less than 10 degrees, then we can do small angle approximations. Along with small angle approximations, we can also make some adjustments, recognizing that if this theta is really, really, really small, and imagine you're looking at the wall and you're seeing those 2 points, and they're really close to each other, and try to imagine the triangle, and actually do it with one eye closed so that we actually have a triangle. Try to imagine the triangle between the 2 points on the wall that are really close together and your eye. It almost doesn't even feel like it could be a right triangle. But because of how close the hypotenuse and one of the sides are to each other, because they're both traveling to your eye, we can make some other approximations such that this theta is equal to, by approximation, S over D. Right? We can say sine of theta is equal to S over D, but because of small angle approximations, theta is equal to S over D. So actually, yeah, sine of theta is equal to S over D technically, but because of small angle approximations, we're okay to see it like this. So if we don't have theta, we can identify the angle between the 2 points by recognizing the distance between the 2 points and the distance from our aperture to the points. And so if we use our eye or a telescope to resolve two images, it depends on how far they are apart or the angular separation between the two. If there are twice Rayleigh's criterion or 1.5 times Rayleigh's criterion, then this will produce fully resolved images. So those are definitely 2 points. If they are right at Rayleigh's criterion, this is just resolved. And just remember, just resolved. And then if they are half or less than, if the theta is less than Rayleigh's criterion, then they are not resolved. We see that as one image. And so we have to kind of play around with the situations to make sure we can identify the angular separation, either by it given to us, but most likely from some sort of distance measurements S and D, and then compare that to what we're using to measure with and what wavelength we're trying to measure, lambda and B, to check to see if we can see two images. So I think we're ready for a gear up problem, because we have recognized that diffraction grating allows us to see different bands of light at different angles. And because we want to improve our ability to see different wavelengths or see different objects, we need to learn how to improve our technology so that we can see better images, or for us as humans to see things. This can be done by resolving different wavelengths, for example, from stars, to identify which wavelengths can we actually observe. Are we seeing one wavelength of light, or actually seeing two very close wavelengths of light? And so by improving our diffraction grating, we can have the ability to do that. Or the ability to see different objects, which we trust a Rayleigh's criterion, in which we use slits or apertures to help us identify where objects are. And if they are too close to each other, their theta, their angular separation is too close to each other, then we see them as one object. And we use this Rayleigh's criteria 1.22 times lambda over B to identify where is the point that they become one object or become two objects to our perception, or the telescope's perception. Okay, let's do a gear up problem. All right, here's a gear up problem for resolving two objects that are far away from you and seeing them as separate. We have two ships that are stranded off the coastline, and their separation is just resolved, so we can actually see them barely as two ships when the Coast Guard observes them with his naked eye. If the Coast Guard's pupil has a diameter of 2 millimeters, what is the minimum angular separation and the minimum of the ships? And assume that the wavelength is 550 nanometers. So I know my wavelength is 550 nanometers, and I know that the diameter of my pupil, or the Coast Guard's pupil, is 2 times 10 to the negative third meters. And that's it. So I use my Rayleigh's criterion, because I know that because it's just resolved, the minimum angular separation means that the angle is equal to 1.22 times lambda over B, right? If the angular separation was greater than this, just resolved, then we would see it as fully resolved, and they'd be even further apart from each other, or closer to your eye. But they are just resolved. So I have theta is equal to 1.22 times 550 times 10 to the negative ninth divided by 2 times 10 to the negative third. And this angle minimum that we found is equal to 3.36 times 10 to the negative fourth. And we have to remember that when we don't use like an inverse sign, and we're using small angle approximations, these are all in radians. That's not degrees, so these are in radians. And you can leave it as radians. It's fine. If you were to convert it to degrees, you would have to multiply to convert to degrees. You multiply by 180 over pi. All right, the next question says, if these two ships are 10 kilometers off the coast of the shore, how far are they apart from each other? So we have to imagine, like, here's our eyeball. That's our eyeball. And these two ships are right here. And so we're looking at them, and that's our distance apart from this. So this is d is equal to 10 kilometers. And what is their s? What is this? Well, because of the small angle approximation, and if I were to like draw this as a right triangle, where this is my angle, then I could see that my tangent, right, the tangent is equal to s over d. But since the small angle approximation, we can say that's just theta is equal to s over d. And we've identified the minimum angular separation for them to be just resolved. Let's assume that's still true. So we still have that value, 3.36 times 10 to the negative fourth, is equal to s over and then 10,000 meters to solve for it in meters. So when I multiply 10,000 to the other side, that's what 1 times 10 to the fourth. So it's going to cancel out the 10 to the negative fourth, and I'm going to get 3.36 meters. So supposedly, if the Coast Guard has those good of eyes, when he looks 10 kilometers off of the shore and sees these two ships as being actually two ships, then the minimum distance apart that they could be is 3.36 meters. If S was larger, then of course he'd be able to resolve them completely. And if S was smaller, they would just look like one ship. But at this level, it's probably just like one dot. Recognizing that this is the angle, the angular separation between them. These problems can get kind of tricky, but if you just focus on the idea of there's a minimum angular separation for something to be just resolved, and noting that s over d is equal to that angular separation, and then using Rayleigh's criteria, I think we can get through it. So I hope this helps, and I'll see you in class.